Welcome back again. We'll begin lesson 4 with a little bit of background, followed by 4 axioms of engineering mechanics. We'll begin with a little background of what we mean by an axiom and so on and so forth. When we say an axiom, we mean it is a self-evident truth. Self-evident truth. And when we say self-evident truth, it really doesn't require any proof. No proof needed. We'll just accept that these axioms are true. And so is the case with Newton's laws that we are going to see later. Okay. Of course, the truth of this Newton's law was amply demonstrated by Apollo mission in 1961. Okay. Now if you see mechanics, we saw that we have two branches to it, statics and dynamics. Okay. The statics is relatively old branch and dynamics is relatively new. This dynamics is relatively new because precise devices for measuring time were not available until very late into perhaps 16th century or so. Okay. Galileo, who lived during 1564 to perhaps 1642, laid foundation for this dynamics by studying masses sliding on inclined planes. Okay, he conducted several experiments and then drew several conclusions or inferences from these experiments. Sir Isaac Newton, during 1642 to 1727, he generalized those results of Galileo in the form of 3 laws of motion. Okay, so profound was the effect of these 3 laws, and also so profound were the other discoveries of Newton, such as Newton's law of gravitation and calculus, which is a mathematical tool that touched every branch of science. We begin our axioms with the 3 laws of Newton. Okay, let us do that. Let us see what are the 3 laws one by one. Okay, Newton's first law says that every body, that is every object, continues in its state of rest or of uniform motion in a straight line unless compelled by an external force. We may see that there are 2 important phrases here: state of rest or uniform motion along a straight line. Uniform motion along a straight line. Okay. What it perhaps says is that everybody will try to retain its state. Okay, so you can see that though this appears a kind of simple looking statement, it defines what we mean by equilibrium. Equilibrium, as inferred from this axiom 1, is either state of rest, not moving at all, or moving with constant velocity along a straight line. And also it defines what we mean by force. Okay, according to this statement, force is any external cause that disturbs equilibrium. So this axiom 1 define what is meant by equilibrium, and it define what is meant by force. Newton's second law continues on this. It has more kind of detail to it as to what is the magnitude of the force. the time rate of momentum is proportional to the external force acting on the body. We saw time rate of momentum is defined by d over dt mv, where m is the mass of the body and v is the velocity. So this law says F is proportional to d over dt mv. Okay, this implies that there exists a constant which satisfies the equation F is equal to k over d over dt mv, where this k is constant of proportionality. Okay. Now for a system with constant mass, you can take that m also out of it and write km over dv, km multiplied by dv over dt, which is km a. Okay, for a system with constant mass, this F is equal to km a. In SI units, 1 Newton of force acting on 1 kilogram of mass produces 1 meter per second square of acceleration. That is, when F is equal to 1, m is equal to 1, a will be equal to 1. So this would say that this constant of proportionality k is equal to 1, and thus F is equal to ma. And this equation F is equal to ma is almost taken as Newton's second law. But we have to be very careful. Newton never said F is equal to ma. He said rate of momentum is proportional to the external force acting on the body. Okay. Now if you really see, if mass is not constant, if you cannot take it out of this derivative over here, then you will have F is equal to d over dt of mv, okay, that is equal to dm over dt of a, dm over dt of v plus m times dv over dt. That is the product rule of differentiation. Okay, this we have to keep in mind. F is equal to ma applies to body of constant mass. Okay, we have seen first law and second law. Let us try to look at third law also. Newton's third law says action and reaction force between two bodies are always equal and oppositely directed. Though it is loosely said here, we need to add simple word, two touching bodies, that is bodies which are in contact are always equal and oppositely directed. That is, if you have one body which is touching another body and exerting some force, and let us say this is body 1 and the other one is body 2, object 1 and object 2. This object 1 exerts a force on object 2. Okay, this is object 2. Okay, this force, let us say we call it force exerted by object 1 on object 2. Now according to this law, if you have this as object 1, this will also be subjected to a force F21, that is force exerted by object 2 on object 1. You can see that these are oppositely directed, and according to Newton's third law, you have F12 is F21. So safely we can just call this F and F here. Okay, we need to keep this in mind. Whenever two bodies are in touch, if one body exerts a force of F, the other body will exert a force F. If one is what we call action, the other is reaction. Okay, and we'll see the final law, which says that there are two particles of mass m1 and mass m2 separated by a distance r. The force of attraction between them, F, is proportional to m1 and proportional to m2, so it is proportional to product of m1 and m2, and it is inversely proportional to square of the distance between them. So these two would imply that F is some constant g times m1 m2 over r square. This g is the constant of proportionality, which is called gravitational constant. And we should particularly be careful not to confuse with capital G and lowercase g here. This lowercase g is acceleration due to gravity. This g, capital G, is gravitational constant. Okay, with this we come to the end of lesson 4, and basically what we have seen is, we have seen what we mean by an axiom, and we have seen first 4 axioms of mechanics. Thank you very much for staying. Have a good day.